We present our work, Sim-to-Real for Robotic Tactile Sensing, via physics-based simulation and learned latent projections, conducted at NVIDIA and the University of Washington. We present a framework for synthesizing the electrical output of robotic tactile sensors, demonstrated for the state-of-the-art deformable SynTouch BioTac sensor. The framework consists of, first, a 3D finite element model, which maps from contact inputs, such as forces applied by external objects, to the resulting deformations of the sensor. And second, a learned model, which maps from these deformations to the electrical output of the sensor. A fast, accurate method for simulating and synthesizing tactile output would enable capabilities such as testing of closed-loop tactile-based control algorithms in simulation, generation of synthetic datasets for deep learning, training of control policies for reinforcement learning, and, if the simulation is fast enough, execution of online model-based control algorithms with the simulator as the model. However, previous work focused on synthesizing electrical output for the BioTac, including our own, has typically exhibited notable limitations. First, simulations have been accurate, but exceptionally slow, for example, taking upwards of 7 minutes to execute per contact interaction. Second, the learning frameworks have typically been fully supervised. They've required careful experimental setups to make sure that simulated and experimental interactions used for training are essentially identical, and they've been unable to leverage unlabeled data collected in a free-form manner. Third, the frameworks have produced insufficiently accurate predictions of sensor electrical signals for contact with unseen objects. Our work has three key contributions. First, an accurate, fast, and freely accessible 3D finite element model for the SynTouch BioTac. Second, a novel application of self-supervision and learned latent projections to map between mechanical simulations and electrical data. And third, demonstrations of sim-to-real transfer through the accurate synthesis of BioTac electrical output and estimation of contact patches, both for unseen contact interactions. First, we develop a 3D finite element model of the BioTac in an open-access GPU-based robotic simulator, NVIDIA's Isaac Gym. In each simulation, contact between the BioTac and an external object is simulated. The simulator then outputs the deformations of the external surface of the BioTac, as well as contact forces and stress fields if desired. After evaluating various configurations, our final BioTac model consists of a deformable, linear elastic skin, a rigid core, and two fixed boundary surfaces that model the effects of the nail and clamp of the real-world BioTac. Key features of the model are listed below. Here we visualize sample indentations of the BioTac, with the colors representing von Mises stress. However, we do not know the exact geometric and material properties of the BioTac. Thus, we left the elastic modulus, Poisson's ratio, and coefficient of friction of the BioTac skin as free parameters and calibrated them against ground truth data. Specifically, we optimized the parameters to closely reproduce the force displacement profile produced by an experimentally validated model from a commercial solver for a particular shear-rich indentation of the BioTac shown here. This experimentally validated model was developed in our previous work, cited below. After calibrating our model, we validated its performance by executing 358 additional indentations with 8 indenters. These indentations were also executed using the experimentally validated model in our previous work. A sped-up recording of some of the indentations in Isaac Gym is shown here. Our simulations with Isaac Gym executed 75 times faster than those in our previous work that used the commercial solver, now running at an average of 5.6 seconds per indentation. The Isaac Gym model closely predicted the force displacement profiles and deformations of the experimentally validated model over the wide range of indentations and indenters. 6 randomly sampled indentations from 6 different indenters are shown here. After validating the model, we matched each indentation with corresponding BioTac electrical data from our previous work to form a labeled dataset used in a later step. With our calibrated and validated simulator in hand, we generated a large amount of finite element data from randomized interactions of the BioTac with 9 additional objects. We also generated electrical data from the BioTac through randomized interactions of the real-world sensor with real-world versions of these objects. These datasets are unlabeled. In other words, we do not know correspondences between the finite element data and the electrical signals. Here are some short videos depicting some of these randomized interactions in both the simulator and the real world.
To learn a mapping between the simulated mesh deformations and the real electrode signals, we first compress information in them using autoencoders. Specifically, we train a graph convolutional neural network to encode the simulated mesh deformations. We compress the XYZ node displacements from 4000 vertices to a latent space of 128 dimensions. We can see that the reconstruct deformations are similar to deformations from the input side. We train a fully connected network to compress the electrode signals from 19 dimensions to 8. Here again, we can see that the predicted electrode signals are similar to the ground truth electrode signals. We then learn a mapping between the two latent spaces using the labeled dataset from our previous work. We learn the mapping as two separate networks. One to map from the mesh latent space to the electrode latent space, and the other to do the inverse projection. We use a standard L2 loss between the predicted latent vector and the ground truth latent vector in these two networks. Our method can now be used to generate BioTac electrode signals from simulated interactions. Given a simulated scenario, we can project the mesh deformations to the mesh latent space using the mesh autoencoder. This can then be projected to the electrode latent space using the learn mapping. Once we are in the electrode latent space, electrode signals can be synthesized using the electrode decoder. We can synthesize electrode signals on unseen trajectories using the mentioned pipeline. We see that our method follows the ground truth signal, while the fully supervised baseline has spikes and also misses small features. Here are results of our method synthesizing electrode signals from simulated BioTac deformations on an unseen object. Our method is less noisy compared to using a direct mapping. This is visually shown in the fully supervised graph, where the thick red line is because of noisy predictions. We can also use our approach to synthesize BioTac mesh deformations from real-world interactions. So, given a real-world interaction, we get the BioTac electrode signals. We then use our electrode encoder to get to the electrode latent space, and then use our inverse projection mapping to go to the mesh latent space. And then we can decode to the mesh deformations using the mesh decoder. Here, we show the accuracy of a deformation prediction on a seen object, but on an unseen trajectory. Our method synthesizes contact regions accurately, but loses accuracy in magnitude as seen by the difference in penetration depth. We can also synthesize deformations on unseen objects. Here again, we see that our method can localize the contact region accurately. Here is another example of a method working on a ring-like object, which was not seen in the training set. We cannot reconstruct the interior circle of the ring indentation, but can still accurately estimate the contact patch. An example application of a method is to synthesize sensor deformations from real interactions, as shown here. We use different pegs to interact with the sensor. The measured electrode signals can be fed into a method to obtain mesh deformations, which are shown on the right. We see here that when the user presses on a particular region on the BioTac, the same region on the mesh deformation side also shows penetration. This is the first time we have been able to reconstruct these kind of deformations for unseen objects from BioTac electrode signals. Thank you for listening. Visit our website for more information.